The last type of diode circuit that we're going to look at is a clamper circuit. And so what a clamper circuit does is it's shifting the entire waveform either up or down by some DC level. And so why would this be relevant? Well, one example would be sometimes when you're transmitting signals, the DC components can be lost, so we can use clampers to restore that DC level. And so you'll learn about some of these signal transmission schemes in a later class where you're looking at communications. But for now, let's just consider a really basic clamper circuit. So about as basic as we can get is something like this, where we just have a sinusoidal voltage source VI, a capacitor, and a diode. And so for this case, we're going to assume that we have a cut-in voltage of 0 and an RF value of 0 as well. We, of course, could add in a V gamma and even an RF, and it's not going to change the overall behavior too much. So that's why we want to just consider this as with values of 0, just to get a general understanding of what the circuit is doing. So let's consider the case of the input voltage greater than 0. So again, this is a sinusoidal input. So when it's greater than 0, if our cut-in voltage is 0, we have a positive voltage up here relative to this terminal. So our diode is going to be on. So our diode is conducting. And if our diode is conducting, essentially that means we are allowing current to flow through this loop, which means that our capacitor is going to be charging up. So capacitor charges up. So implicit in that is we're assuming that our capacitor was initially uncharged and then we connect it to this input sinusoidal source. Okay, so once we reach sort of the crest of our sinusoidal input, ideally when we first leave that, our capacitor is going to be charged up to the maximum. So VI, so when our VI begins decreasing, we're going to say that ideally our VC is equal to VI max, or whatever the magnitude is of that sinusoidal voltage. Now, we can make another assumption that's, again, going to make our analysis a little easier, even though a little less accurate. And we can say, let's assume that this value stays constant. So let's assume VC stays constant after charging up. And so that's not a terrible assumption. So let's say we attach some load resistor where we have V out written above in the circuit here. So if that time constant associated with that, so if our tau with C and RL is much greater than our input frequency on our Vin, then assuming that our Vc is constant is a pretty good assumption. So we're going to assume that's the case, again, just to make things a little more simple. And we could refine that later if we needed to. So then what we can do is we can come back up to our circuit and we can look at a Kvl loop, and we can say in general V out is equal to negative Vc plus Vi. So we can say in general we have V out is equal to Vi minus Vc, so I've just switched the order from what I said before. And to sort of keep that where we said our Vc is already charged up, we can say after that point we have Vi max times sine of omega t for our input voltage, and then minus our Vc, which is just staying constant at that Vi max. So that's a little bit hard to follow, I think, just looking at words and the circuit diagram. So let's take a look at what this looks like graphically. So here I have our Vi, so we're saying this is some sinusoidal input that's going between some Vi max and negative Vi max. Well, what we're saying with our capacitor voltage, so let's make our capacitor voltage green. So our capacitor voltage with 0 V gamma is just tracking this right away, and it's charging up until we get to some maximum value Vi max. Now, as we talked about with our ripple voltage, as we saw, this would probably be decaying Depending on the time constant of the load, we have to compare that to the frequency. How fast is it going to start charging up again? But in this case, what we're saying is let's assume that that time constant for the capacitor and the load is really large, such that it's discharging so slowly that we can basically just assume that it's constant from here on out. And so maybe if we zoomed in on some part in here, what we would see is it's going like this, and then it starts charging up again. And then over here it starts discharging and charging up again, but it's so small that it basically just looks like a straight line. And so this would be our capacitor voltage VC. So now remember, in general, we said that our Vout is equal to Vi minus Vc. So let's come in here and add our Vout then. So let's do that in red. So what our Vout is going to be is, of course, for this first section here, the two are the same. So we're just going to have a Vout that is 0 for that initial capacitor charging up. Now, beyond that, we're just subtracting the constant value of Vi max. So we get something that looks like this. So it's the same shape as our Vi, it's just dropped below. And so let me try to do that a little bit better. So let me give myself a few points here to shoot for. So we get something that looks like this. So the same shape, just dropped a value of Vi max. And so that sinusoid would just have been clamped down by Vi max. So now the minimum value down here would be negative 2 times that maximum value. So it's oscillating between negative Vi, or sorry, not negative Vi max, between 0 and negative 2 Vi max, with a mean value of negative Vi max, which is how much it's been clamped downwards. Now, real briefly, a couple things that we can talk about changing the circuit to get different behavior from our clamper is if we change the orientation of this diode. So if we flip the diode such that the arrow is pointing up, we would then be clamping our waveform up. So we would be moving this red waveform above. We'd be adding Vi max to the output. So let's write that. So we can clamp up by changing our diode direction. And then one other thing that we can do is we can also include DC sources in the circuit to clamp to different levels. So we can include DC sources to clamp to different levels. And so if you want to see an example of that, you can look on page 95 in the textbook, and that explains that in a little more detail. So this is the last type of diode circuit that we're going to look at in this course. Of course, that does not mean that this is the end of all of the diode circuits. There are, of course, plenty other types of diode circuits out there. In fact, we're going to look at a lot of them in a later class when we look at different types of power supplies. But hopefully what we've done with these videos in this unit are sort of expose you all to some of the most common and most practical types of diode circuits.